we are discussing applications of transmission lines. We saw the application of transmission line for measuring the unknown impedance at high frequencies. As pointed out, at high frequency the measurement of phase is not very reliable. So, one would like to estimate the phase indirectly without doing the direct measurement of the phase. So, as we saw, by using transmission lines, just by measuring the magnitude of the voltages on transmission lines, we can find the voltage standing waves, their parameters, and from that we can indirectly estimate the phase of the unknown impedance. The another application which we are investigating is the transmission line as circuit elements. We saw that if we take a section of a transmission line which is either open circuited or short circuited, then these sections of transmission lines can be used as a reactive element in the high frequency circuits. So, last time we saw the characteristics of the short circuit and open circuited sections of transmission lines, and we also saw that these sections, if the length is multiples of lambda by 4, then this section can be used as a resonant circuit in the high frequencies. So, essentially by taking a length of a transmission line which is either lambda by 4 or lambda by 2, we can realize a parallel or series resonant circuit. We saw that if the input impedance of this line is close to 0, then the circuit behaves like a series resonant circuit. If the input impedance of the line is close to infinity, then the line behaves like a parallel resonant circuit. And once the circuit behaves like a resonant circuit, then the natural question to ask is, what is the quality factor of this resonant circuit? And that is the thing essentially we are investigating now, that if I consider this section of a transmission line as a resonant circuit, then what is the quality factor of this resonant circuit? As mentioned earlier, that whenever we talk about resonant circuit, the quality factor is related to the losses in the resonant circuit. However, up till now we have considered the line to be lossless. So, by definition, for a lossless line the quality factor is always infinity. Now, since we are investigating the quality factor, no matter how small the loss is in the transmission line, we have to account for that loss, then and then only we will be able to get the correct answer for the quality factor. So, we investigate now the input impedance of the transmission line when the length is multiples of lambda by 4, and from there then we find out the quality factor of the resonant sections of transmission line. Having said that, let us consider now a specific case that the length of the line is lambda by 4, either the line can be open circuited or short circuited. So, the length which we have called last time is LSC, which is the length of a short circuited line. This length is now lambda by 4. Similarly, LOC is also lambda by 4. So, since the length is lambda by 4, and as we have seen that the impedance, normalized impedance inverts itself every distance of lambda by 4, this open circuit will appear like a short circuit in the line. The short circuit will appear like an open circuit after a distance of lambda by 4. So, this line, if the length is lambda by 4, will appear like a parallel resonant circuit, whereas this line, if the length is lambda by 4, will appear like a series resonant circuit because the impedance will be very close to 0. So, now specifically we just consider the sections of transmission line which are having length of lambda by 4 and find out its input impedance, and then go to the calculation of the quality factor. In general, since we are considering loss now, the input impedance of the open or short circuited line has to be written in the total propagation constant gamma and not only the phase constant. So, if you go back to your original impedance relationship which we have derived and substitute ZL equal to either 0 or infinity depending upon whether a short circuit or open circuit, I get the input impedance. So, this is the input impedance for a line of length L when the line has a loss. So, let us call for an open circuited line, let us say this is denoted by ZOC. So, that is equal to Z0 cot hyperbolic of gamma L, and for ZSC, the short circuited line, that will be Z0 tan hyperbolic of gamma L, where if you remember gamma is equal to alpha plus j beta. The line is low loss line, so alpha is much smaller than beta, as we have considered earlier. When the line is lossy, the propagation constant now is alpha plus j beta, and it is not only j beta. We still assume that the characteristic impedance of this line is almost real. So, although we have said now the propagation constant is complex, it is not purely imaginary, the Z0 we still consider to be almost real. So, now what essentially we are saying is, consider any of these cases, the open circuit line or a short circuit line, and under the assumption that alpha is much less than beta, okay, and the length is either multiples of lambda by 4 or any arbitrary length, find out under this approximation what will be the input impedance. We know if you consider a short circuit line and if the length is lambda by 4, it should appear ideal like open circuit. Similarly, if you take an open circuited line and take a length lambda by 4, the input impedance will be like a short circuit. However, in the presence of the loss, that will not be true. So, the impedance will neither be infinity nor it will be 0, and that is what we are trying to calculate now, that if the loss is present, what will be the input impedance of these two lines. So, let us consider this ZSC and substitute for gamma alpha plus j beta. So, from here I can get ZSC, that is equal to Z0 tan hyperbolic of alpha plus j beta into L. I can expand this, so that will be Z0 tan hyperbolic alpha L plus j tan beta L divided by 1 plus tan hyperbolic alpha L j tan beta L. So, in general, for a length of a line, the input impedance, short circuited line, the input impedance essentially is given by this. Now, since alpha is small, for a length of lambda by 4 section of transmission line or a length which is smaller than lambda by 2, this quantity alpha L is much smaller than 1. So, we have alpha L much smaller than 1 for a low loss line. Once I get this, then I can make an approximation that tan hyperbolic alpha L will be approximately equal to alpha L. So, if I substitute that, then the input impedance of a short circuited line ZSC will be approximately equal to alpha L plus j tan beta L divided by 1 plus j alpha L tan beta L. Now, if the line is short circuited and if the length is lambda by 4, this L is equal to lambda by 4. So, for L equal to lambda by 4, beta L will be 2 pi by lambda into lambda by 4, that is equal to pi by 2. So, if I substitute now the length of the line equal to lambda by 4, this quantity will be infinity, this quantity will be infinity. So, I can take this tan beta L common of infinity. So, what will I see, that ZSC will be equal to, if I take j tan beta L common, this will be alpha L divided by j tan beta L plus 1 divided by 1 upon j tan beta L plus alpha L. Substituting now for beta L equal to pi by 2, that means tan beta L is infinity, this quantity will be 0, this quantity will be 0. So, I will get ZSC is approximately equal to 1 upon alpha L. So, the input impedance of a short circuited line, if the length is lambda by 4, this is short circuit, this length is lambda by 4. Ideally for this line it should have appeared open circuit at the input, this is this impedance ZSC. Now, I do not see open circuit, but I see an impedance which is very large because alpha L is very small quantity for a low loss line, but this impedance is not infinity. So, a short circuited section of a transmission line of length lambda by 4 does not in practice appear open circuit, but it has some impedance measured at the input terminal, which is essentially this. Similarly, if I had done the similar exercise for the ZOC and it did the expansion and all those similar things if I had done, then the input impedance of open circuited line would appear to be alpha L multiplied by Z naught. Anyway, here we have to put a Z naught here. So, this quantity should be multiplied by Z naught, this is Z naught, this is Z naught. So, doing the same exercise for the open circuited line, this is lambda by 4, this is open circuit. So, the impedance which we measure here is now ZOC. So, by doing the same exercise as we have done for the short circuited line, the ZOC will be approximately equal to Z0 into alpha L. So, for a short circuited section of a transmission line, the input impedance is Z0 divided by alpha L. For a open circuited section of a transmission line, the impedance is Z0 multiplied by alpha L. So, what we now note here is that the input impedance of a resonant section of a transmission line is ideally infinity or 0 depending upon the resonant circuit is a series circuit or a parallel resonant circuit. However, in practice we see a large impedance for a parallel resonant circuit and a small impedance for a series resonant circuit. Once you get this, either I can use this information that if I vary now the frequency around the resonant frequency, how this impedance changes, from there I can get the impedance variation as a function of frequency or what is called the frequency response of your circuit, and from there I can calculate the quality factor of the circuit. So, quality factor can be calculated in two ways. One is from the frequency response of the circuit. Secondly, it can be calculated from the basic definition of the quality factor. So, let us see what is the quality factor by definition. So, the quality factor Q is defined as 2 pi multiplied by the energy stored in the circuit divided by the energy loss per cycle. Loss per cycle. If the resonant frequency is f naught, the energy loss per cycle is, there are f naught cycles per second. So, I can write down the same expression for the quality factor as 2 pi into the resonant frequency of the circuit multiplied by the energy stored in the circuit divided by the energy loss per second, which is nothing but the power loss in the circuit. So, this is divided by the power loss in circuit. So, to calculate the quality factor, if I find out what is the energy stored in the section of a transmission line. If I calculate what is the power loss in the transmission line, then I can find out what is the quality factor of that section of a transmission line. Alternatively, as we mentioned that the quality factor is related to the frequency response. So, if I plot the variation of current or voltage when a voltage or current source is applied to the input section of a transmission line and measure the 3 dB bandwidth of the response, the center frequency divided by the 3 dB bandwidth of the frequency response gives me the quality factor. So, if I have a frequency response of this circuit, which is, so this is my impedance as a function of frequency, I get a frequency response which will look typically like that. Depending upon whether I am using series or parallel resonant circuit, this will be the voltage response or the current response, but at resonant frequency I get the maximum response, and as I deviate from the resonant frequency the response drops. So, I can measure the 3 dB frequency for this response, where the amplitude reduces to 1 over root 2 of its maximum value if I take the amplitude response. So, this is the delta f, which is the 3 dB bandwidth. Then the quality factor for the circuit is equal to f naught divided by delta f. So, now the quality factor can be calculated from the impedance calculation, because the impedance can give me the frequency response. Alternatively, take a section of a transmission line, find the voltage distribution on the transmission line and the current distribution on transmission line, find out what is the energy stored, find out what is the power loss in the transmission line, and use this definition to calculate the quality factor. Let us go to this first method, which is the more fundamental method of calculating the quality factor for transmission line. So, let us say I consider specifically a section of a transmission line which is of lambda by 4 length, and let us say the line is short circuited. So, let us take a specific case here. The line is short circuited, this length is lambda by 4, and since I am not talking about the resonant frequency, the length cannot be lambda by 4 at all frequencies. So, let us say this is having a specific frequency lambda 0 by 4, where lambda 0 corresponds to the wavelength of the resonant frequency. So, this length is lambda 0 by 4. So, the resonant frequency of the circuit f0 is nothing but the velocity of the wave divided by the length lambda 0. Now, we can get the voltage and current expression on this transmission line with the load short circuited, and when the load is short circuit, the reflection coefficient at the load point is -1, we have seen earlier. So, reflection coefficient load gamma L, that is ZL minus Z0 divided by ZL plus Z0, and ZL is now short circuit. So, ZL is 0, so that is equal to minus Z0 upon Z0, that is equal to -1. So, the reflection coefficient for short circuit load is -1, which is saying that the amplitude of reflection coefficient is 1 and it has a phase change of 180 degrees. We will make use of this information later when we go to the application of transmission line for the voltage or current stepping of transformers. But at this point, once I know the reflection coefficient, I can write down the voltage and current equation, and I can find out what is the variation of the voltage and current on the transmission line. Going to the basic equations of the voltage and current, the voltage now on the transmission line can be given as V plus e to the power j beta L plus V minus e to the power minus j beta L. But for reflection coefficient of -1 at the load, this quantity gamma L is nothing but V minus divided by V plus. So, if I substitute for V minus is equal to minus V plus, the voltage on the line is essentially given by this. I can combine this, I can take V plus common. So, this is e to the power j beta L minus e to the power minus j beta L, which is nothing but j 2 into sine of beta L. So, the voltage on transmission line can be j 2 V plus sine of beta L. Since there is nothing very special about this parameter V plus, I can combine 2 V plus to define another quantity which is V 0. So, the voltage magnitude on the transmission line is magnitude of V 0, some voltage multiplied by sine of beta L. Similarly, for the current, if I substitute for the reflection coefficient equal to minus 1, the current on the transmission line will be given by this, which again by combining these two terms I will get as V 0 divided by Z 0 multiplied by cosine of beta L. So, if I plot now these voltages on the line, say this is now lambda 0 by 4 line, this is short circuit. So, the voltage is 0 at this point because this variation is sine of beta L. So, at L equal to 0, which is at the load, the voltage is 0, and when I go to a distance of lambda by 4, this quantity beta L becomes pi by 2. So, this quantity is 1. So, I see the voltage which is V 0. So, I get a voltage variation which is a one cycle variation from load point to the input point. So, this voltage here is V 0 and this point is 0. So, this is the variation of magnitude of voltage on the transmission line. Similarly, if I plot the current has a variation which is cosine variation. So, at L equal to 0, this quantity is V 0 upon Z naught, and when L is lambda by 4, that time this quantity will be 0. So, I will get a current variation which will go like that. So, this is mod of V plus divided. This length is lambda 0 by 4. So, I know now on the section of this transmission line the voltage and current variation, and once I know the voltage and current variation, then I can find out what is the capacitive and inductive energy stored at different locations on transmission lines. So, if I take a small section of transmission line, the capacitance of the small section of transmission line is C multiplied by the length of the line dl. As we discussed in the very first lecture, that for a small section of a transmission line, we define the capacitance as the capacitance per unit length multiplied by the length of the section of the transmission line. So, for a section of a transmission line of length dl, the capacitance is C into dl. So, the capacitive energy stored in that section of a transmission line is half C into dl into the voltage square at that location. Similarly, I can get the inductive energy located in that infinitesimal section of a transmission line. So, once I get that, the total energy stored in the transmission line can be written as, so this is the total energy stored, let us call that U, that will be equal to half C. Total energy will be the integrated version over the length of the line. So, this is from 0 to lambda 0 by 4 mod of V into L square into dl plus half L. So, again this is lambda 0 by 4 mod I of L square into dl. Substituting for voltage and current, this is sine of beta L, this is cos of beta L. So, this is half into C integral 0 to lambda 0 by 4 mod of V 0 sine beta L square dl plus half L integral 0 to lambda 0 by 4 V 0 upon Z naught cos of beta L square into dl. These integrals are very straightforward. You can calculate the value of this integral, and that will be equal to 1 upon 4 C V naught square into lambda 0 by 4 plus 1 upon 4 L V naught square upon Z naught square into lambda 0 by 4. Now, since Z naught we know is square root of L upon C, the quantity L upon Z naught square, this quantity is nothing but C. So, what we find is that these two terms are equal. What that means is that the energy stored in this resonant circuit is equally distributed into the capacitive energy and the inductive energy. So, this term is represented the energy stored in the inductance of the line, this term shows the energy stored in the capacitance of the line, and from here we see these two quantities are equal. That means the energy stored in the inductance and capacitance of line are equal. If I substitute for this, then the total energy stored will be nothing but twice of this term or twice of this term, because these two terms are equal. So, I get the total energy stored now U, that is equal to half into C V naught square to lambda divided by 4, lambda 0 divided by 4. This is the total energy stored in the transmission line. For calculation of the quality factor, now we require the power loss in the transmission line. One way of doing that is, again you go to the primary parameters, that the resistance and the conductance of transmission line, and get the voltage and current on the transmission line, again integrate it along the transmission line to find out the I square R losses. But we can do something different here to get the loss, and that is, if I take a section of this transmission line here, the energy source is connected to the line here. So, if I find out the what is power loss at this location, this power loss will be nothing but the power lost in this line, because the line is short circuited at the other end. That means the load is not consuming any power. So, if at all any power is supplied to this power will be only equal to the loss which has taken place inside the section of this line. So, without going into the primary constants of transmission line, just by calculating the input impedance of this line, we can find out what will be the equivalent resistance to which the power is supplied, and from there we can calculate the loss of power in this section of transmission line. Precisely that is what we do now. So, we say that since the line is short circuited, the input impedance which will be seen here will be Z0 divided by alpha L. So, the input impedance of this line, you have seen earlier, this is ZSC is approximately equal to Z0 divided by alpha into L, where L is equal to lambda 0 by 4. So, now the power loss in the transmission line, let us say we call it P loss, that will be equal to V naught square, because that is the voltage which you are seeing at the input terminals here. So, it is as if I am having a voltage source of V naught here, which is supplying power to a resistance whose value is this. So, I get the power loss, which is V naught square divided by the R, which is Z naught divided by alpha L. So, this is equal to your V 0 square divided by Z naught into alpha into L, which is equal to lambda 0 by 4 in this case. So, this is lambda 0 by 4. Once I know the energy stored in the circuit and the power loss in the circuit, then I can get the quality factor Q, that is equal to 2 pi into F 0 into energy stored in this circuit. So, this is half C V naught square lambda 0 by 4 divided by V 0 square upon Z naught alpha into lambda 0 by 4. So, this quantity cancels, V 0 square cancels. So, essentially we get this equal to 2 pi F 0 Z 0 C divided by 2 alpha. Now, we can do some small manipulation, because you know this Z 0 is square root of L by C. If I write this quantity here, Z 0 into C, so Z 0 into C will be square root of L upon C into C. So, that is equal to square root of L C, and the quantity here 2 pi into F naught is nothing but omega. So, the numerator now in the quality factor Q is omega square root L C divided by 2 alpha, where omega is nothing but 2 pi into the frequency. Now, if you recall, this quantity omega square root L C is nothing but the phase constant of the transmission line beta. So, this quality factor Q is beta divided by 2 alpha. Same expression you can obtain, as I mentioned, by finding out the frequency response of the section of a transmission line. So, if I had measured the impedance and measure the variation of the impedance as a function of frequency, I can find out the 3 dB bandwidth of the circuit, and then from there, using the definition that the quality factor is the resonant frequency divided by the 3 dB bandwidth, I will get the same expression for the quality factor. So, now the quality factor is now related to the phase and the amplitude constant, or the phase and the attenuation constant of the transmission line. And for a low loss line, since beta is much larger than alpha, this quantity is very large. So, for low loss line, beta is much greater than alpha. So, Q is much greater than 1, and that is a very useful property, that when we go to high frequencies, a section of a transmission line can really give me a very high quality factor circuit. And since, as we mentioned, the quality factor is related to 3 dB bandwidth, higher the quality factor, smaller is the 3 dB bandwidth, or more tuned the circuit is. So, the frequency selectivity of a circuit is very good if the quality factor of the circuit is very large. So, for the low loss section of a transmission line, since the quality factor is large and typically you can get a few hundred megahertz, the quality factor could be as high as few hundred or thousand, you can really get a very good frequency selectivity by the sections of transmission lines used as the resonant circuits. That is the reason when we go to the high frequencies, the sections of transmission lines serve very good purpose for realization of the resonant circuits. So, this is one of the very important application of transmission line, right, in the high frequency circuit. The next application of the transmission line is the voltage or current stepping up transformer. So, the third application which we have here is voltage or current step up transformer. Let us again consider a quarter wavelength section of a transmission line which is shorted at one end and open circuited at other. So, let us say I have a line and let me draw a little bigger picture here. So, this is short circuited, this end of the line is open circuited and this length is lambda by 4. Let us say by some means some voltage is induced on some point on this section of transmission line. So, let us say at some location here some voltage is induced. If I consider a voltage source connected to this at this location, it will see as if there are two sections of transmission line connected in parallel, this section and this section. Now, since the standing waves still are not set up and just voltage is just getting induced inside the transmission line, this voltage does not see any other impedance but the characteristic impedance of the line. So, as soon as the voltage tries to get induced inside the structure, it sends two travelling waves on both sides of the section of transmission line, because it will see as if the energy is supplied to the characteristic impedance on these two transmission lines. So, essentially two equal amplitude waves are sent from this location. This wave now travels up to this point. When it reaches here, this wave sees a short circuit. It means you see the reflection coefficient of -1. So, this wave here is reflected completely from here with a reflection coefficient of -1, that is magnitude is unity and the phase is 180 degrees. So, here I have a reflection coefficient gamma that is equal to -1, so is equal to 1 angle pi. So, this wave which was travelling here rightwards, after reflection undergoes a phase change of pi. This wave now travels all the way up to open circuit. I am considering only this wave. So, it wave comes here, it gets reflected from the short circuit point, travels all the way up to the open circuit point. At the open circuit, again the reflection coefficient is +1, its magnitude is 1, its angle is 0. So, again the entire wave from here gets reflected with no phase change and it reaches to this location. So, by the time this wave has travelled a round trip from here to here, it has travelled a distance of lambda by 2 and has gone an additional phase change of pi because of this reflection coefficient here. Now, a distance travel of lambda by 2 corresponds to a phase change of pi plus a phase change of pi which is taking place because of the reflection coefficient here. So, this wave which travels a round trip and reaches here has undergone a phase change of 2 pi. That means, the wave which is getting induced at this location C is now a phase which is of the wave which is reflected same as the wave which is getting excited, or in other words is some kind of a positive feedback which is going on now. The induced voltage and the voltage which has gone on this after round trip, they add up. So, the two voltages together now start traveling on this. When they again come after round trip, it is again in phase. So, the induced voltage again adds to this voltage. So, the voltage essentially starts growing on the transmission line. Exactly same thing happens to this wave also. This wave will go like that. After reflection from here, it will not undergo any phase change, but the entire power will be reflected. It will travel a distance of lambda by 2. This wave again see a reflection coefficient of -1 here. So, this wave also will have a regenerative process. So, this wave will grow in amplitude, this wave will grow in amplitude exactly same way, and the standing wave of this line will grow, because the two waves are equal in amplitude and they are going exactly the same way. So, we will develop the fully standing wave of this line because of a small induced voltage at this location. One may wonder then how far this growing of the wave will go on. In fact, if there are no losses in the transmission line, this growth of the wave will go up to infinity. So, the voltage will go on growing for infinite amplitudes, because there is no controlling parameter on the transmission line. So, even if a small voltage is induced on a transmission line for some stray coupling or something, and if the section of transmission line is resonant, then the voltage which you see on this transmission line is now much larger compared to the induced volt because of this regenerative feedback. So, this process now can be used for your advantage, that the voltage which you measure on transmission line could be much larger compared to the coupling voltage at this location. Or in other words, this resonant section of a line can be used as a voltage stepping up transformer. Precisely this is the application we are talking about, that take a voltage source which is a small source which you connect to this resonant section of a line, and if I measure the voltage on the open circuit of the line, this voltage will be much larger compared to the coupling voltage on the line. So, if there is no loss of the transmission line, ultimately in the steady state the voltage will reach to infinity between the terminals of the line. However, in practice it does not happen, because when the voltage and the current starts growing on the transmission line, the ohmic losses also go on increasing, and when the loss in the line because of the resistance and the conductance becomes equal to the energy supplied by the coupling source, at that point there is an energy balance now, and the growth of the standing wave on this section stops. But before this stage reaches, the voltages and currents have already reached to a substantially high value. So, even in practice, when the losses of the transmission line are small, one may generate very large voltages and currents, voltage here and the current here, by a small coupling source connected to the section of a transmission line. So, this application is a useful application whenever we want to step up the voltages and currents at high frequencies. One can show that the voltage which is going to grow, that is related to the quality factor of the transmission line. So, again the high quality factor means low losses on transmission line, and that will give me the higher voltage on the terminals of the transmission line. The phenomena which can be used for your advantage for stepping up the voltages or current could be harmful also in many cases. Consider an application where a small energy source gets unwillingly coupled to the section of transmission line, and if the section of transmission line is of resonant length, then the voltages which will develop on this line will be much larger, which your electronic circuit can handle. So, any small coupling of the energy to a resonant section of transmission line may unknowingly develop the voltages which will be much larger compared to what the circuit can handle, and it is possible that your electronic circuit can get damaged because there are very large voltages which are developed here. So, while doing the design of the high frequency circuit, it should be kept in mind that no sources get coupled to the sections of transmission line, especially if they are of resonant length. Otherwise, you will unknowingly you will be developing very large voltages at some locations, right, in the circuit, which might be harmful to the electronics which are employed in high frequencies. So, the phenomena of stepping up voltages and current could act as a deterrent when a unknowing voltage source or current source get coupled to the section of a resonant transmission line. These are certain applications now which are for designing the high frequency circuits, and as I mentioned earlier, the sections of transmission lines are used for high frequency circuit designs. So, whenever we have a high frequency circuit design, especially at microwave frequencies, we rarely see the component like capacitances, inductances. What we see are the active devices like transistor, FETs, and the reactive components are completely realized by the sections of transmission lines. So, most of the microwave circuits will appear as some arbitrary sections of transmission lines connected here and there across the active devices. So, the sections of transmission line play a very important role in the design of the high frequency circuits.